Your landing zone was designed for a world that doesn't exist anymore. It was designed in 2018, and it was built on an assumption that hasn't aged well. The assumption was simple. Total standardization equals total control. Lock everything down. Enforce one way of doing things. Centralize the decisions. Reduce variation. Reduce risk. In theory, it made sense. In practice, it broke everything. Because here's what actually happened. You standardize so hard that infrastructure provisioning now takes weeks. Teams hit a policy wall. They can't get what they need through official channels. So they solve the problem a different way. They spin up personal Azure subscriptions. They use their own credit cards. They adopt SaaS that lives outside your cloud footprint entirely. You wanted control, but you created the exact opposite. You created shadow IT. Your landing zone isn't failing because it's too permissive. It's failing because it's too slow. This isn't a security problem. This is a governance problem. And the governance problem lives in the code, in how you designed your Bicep templates, how you structured your management groups, and how you decided which decisions would be centralized and which would be distributed. You built rigidity into infrastructure as code, and now you're watching teams build parallel infrastructures just to get around it. We're moving from static templates to living infrastructure. That shift changes everything. Not the Bicep syntax, not the Azure services. The shift changes how you think about governance itself. It moves from how do we control what people do then to how do we make the right path the easiest path. That's what this deep dive is about. The governance model behind the code. Landing zones aren't architecture. They're organizational power structures expressed as Bicep. That's the reframing that matters. Most people treat landing zones as a technical blueprint. They look at the network topology, the subscription structure, and the naming conventions. But they're missing the real story. Every decision encoded in those Bicep templates is actually a decision about who gets to decide things, who can create a resource, who approves policy changes. How fast can a team get what they need? Those aren't technical questions, they're organizational questions, and they're baked into the code. There are two models of governance operating in most enterprises right now. The first is gatekeeper governance. Central IT owns the Bicep templates. Central IT reviews all changes. Central IT approves all exceptions. Central IT moves slowly because the blast radius of getting it wrong is massive. The responsibility is concentrated. The authority is concentrated. The speed is concentrated slowly. The second model is enabler governance. Central teams define guardrails, not gates. They publish reusable modules. They build self-service patterns. They move fast because the responsibility is distributed. The authority is distributed. Teams can ship within the guardrails without asking permission. But here's the paradox. Gatekeeper governance, designed to reduce risk, actually increases it. Because the more friction you create in the official path, the more teams find unofficial paths. Centralized controls create pressure. Pressure creates shadow IT, and shadow IT is invisible. It's unmeasured. It's unlogged. It's unpatched. It's the opposite of control. The research is stark. Up to 40% of enterprise IT spending now happens outside official channels. That's not a technology adoption problem. That's a governance design problem. There are 3 specific governance failures that drive this. First, slow provisioning. Teams request a new subscription or a new infrastructure pattern, but central IT takes weeks to review it. The teams time out. They build it themselves somewhere else. Second, overly prescriptive policies. The standard template doesn't fit the use case. The request to deviate is denied. The teams build it in personal subscriptions instead. Third, poor visibility into why the rules exist. Policies are enforced but never explained. Teams don't trust the constraints, so they circumvent them. Each of these failures flows from the same structural problem. The governance model assumes control requires centralization. In reality, control actually requires clarity. It requires speed. It requires usability. It requires making the governed path faster than the ungoverned one. Understanding this model is the prerequisite to fixing it. Because you can't fix a governance problem with more governance. You fix it by restructuring how governance decisions flow. From gatekeeper to enabler, from how do we prevent mistakes, to how do we make good decisions, the default. Once you understand the model, everything else becomes addressable. Your subscription strategy, your network architecture, your shared services, your multi-region design. The technical problems are only problems because the governance model underneath them is broken. That's what we're going to fix. The subscription strategy paradox. When you realize your governance is broken, your first instinct is to create distance. More separation, more subscriptions, more isolation. It sounds right on paper. If one subscription gets compromised, the damage is contained. If teams are separated by subscription boundaries, they can't break each other's tools. You're trying to find standardization through multiplication. But in reality, it does the opposite. More subscriptions don't equal more security. They equal a larger surface area for things to go wrong. Because here's the problem. Every new subscription you create is another management group you have to place, and another set of policies you have to assign. You have to set up new login configurations and new identity integrations for every single one. You haven't actually solved your governance problem. You've just taken the mess you had in one place and scaled it across 10. And then the operational cost starts to compound. When you have 3 subscriptions, you can keep track of them. When you have 30, you start losing the thread. You forget which team owns which environment or which naming convention applies to which resource. The separation you thought you were buying turns into total fragmentation. No 2 subscriptions look the same because there is no way to enforce rules across all of them at once. The whole idea of standardization collapses the moment it hits real-world complexity. But here's the deeper problem. Creating more subscriptions doesn't fix a broken governance model. It just spreads the friction around. Teams still can't get what they need through the official process, so they stop asking for new subscriptions. Instead, they ask for access to one that was already approved. Or they find a way to skip the approval process entirely. The strategy itself becomes the reason people look for workarounds. What actually works is a model called subscription vending. Instead of teams filling out a request and waiting weeks for an admin to click buttons, you automate the entire handoff. A team fills out a simple form. They define the workload, the compliance needs, and the owner. That form triggers a Bicep deployment that does the heavy lifting. It creates the subscription, places it in the right management group, and configures the policies and logging automatically. The team gets a ready-to-use environment in minutes instead of months. The difference is profound. You are still making the same governance decisions you were before, but now you are making them once in your code and executing them every time without fail. The strategy becomes predictable. Every subscription follows the same pattern because they all come from the same Bicep template. There is no manual variation and no undocumented exceptions. You don't have to worry about a subscription violating policy because someone set it up who didn't know the rules. The cost difference here is staggering. Slow provisioning isn't just an annoyance for developers, it's a massive security risk. When teams have to wait weeks for official infrastructure, they go shadow. But when a team can provision a compliant environment in under 30 minutes, they stay within the guardrails. That isn't a guess. The research shows that 30 minutes is the breaking point. Faster than that, people follow the rules. Slower than that, they find a different way to get their work done. So the metrics that actually matter are concrete. You need to measure provisioning time, how long it takes from a request to a ready-to-use subscription. You need to track your policy compliance rate to see if your subscriptions actually follow the rules. And you need to look at your time to remediate. When something breaks a policy, how fast does it get fixed? These aren't just infrastructure stats. They are governance metrics that tell you if your model is actually working. And the design principle becomes clear. Don't design for standardization. Design for blast radius. A blast radius is just a boundary. It's the limit of the damage when something eventually goes wrong. A good blast radius is small and easy to recover from, while a bad one is large and catastrophic. Subscriptions are your blast radius boundaries. The question you should be asking isn't, how many subscriptions do we need? It's, what size of failure can we actually recover from? That shifts the entire conversation. Instead of trying to isolate teams with more subscriptions, you start creating the right number of subscriptions to contain failures while letting teams move fast. You stop asking how to enforce standards across subscriptions and start asking how to build those standards into the subscriptions automatically. Once you fix the strategy, once you've automated the vending and made it instant, everything else gets easier. The network architecture and the shared services model finally start to make sense. The whole structure snaps into focus. Because now you aren't designing for control, you're designing for flow, management groups as a governance boundary. Once you've automated your subscription vending, you run into a new challenge. Those subscriptions still need to be organized. They need to inherit the right policies and follow a structure that makes sense. That is where management groups come in, and this is where most teams make a critical mistake. Management groups are not organizational containers. They are policy inheritance engines. Every policy you assign at the top flows down to every child subscription below it. Every RBAC assignment and every diagnostic setting cascades through the levels. It's a waterfall model. And the moment you misunderstand how that cascade works, you've broken your entire governance structure. The mistake is simple. Teams build hierarchies that look like their company org chart. They put the platform team here and the security team there. They build a structure where the platform is at the top, with networking and security as children. It feels organized. It maps to the people who are responsible for the work, except that is the opposite of how inheritance works. When you assign a policy at the platform level, it hits everything below it, including your security and networking subscriptions. If the security team needs to set its own rules for its own subscriptions, those rules sit right next to the platform rules. If they conflict, the rule closest to the resource wins. Now you have policy shadowing. The team that is supposed to own the decision no longer has actual control over it. The problem is that you're designing for reporting lines instead of governance flows. A management group hierarchy should show which decisions belong together, not which manager owns which team. If all your workloads need the same security baseline, they should sit under one group where you can assign that baseline once. If you have different compliance requirements for different apps, they need to be in different branches so the policies don't clash. That is the structural difference. Org charts follow people. Governance hierarchies follow requirements. They are almost never the same shape. And here is the operational consequence. Once you drop a subscription into a hierarchy, moving it is incredibly expensive. The policies it used to have are gone, and it starts inheriting from a new parent. You have to reevaluate every resource against the new rules. You might have to update logging and fix broken RBAC assignments. You can do it, but it takes weeks of validation and carries a high risk of breaking things. The choice you make at the beginning locks you in. You can't easily change it without causing a massive disruption. This is why so many companies are stuck with hierarchies that don't work. They chose the easy path at the start, and now they are paying for it with a system that can't move. The way you design for evolution is different. You have to design for what stays the same and what needs to change. Some decisions are permanent, like your security baselines or your core compliance rules. Those go at the top of the hierarchy and they stay there. Other decisions are specific to a single workload or a temporary project. Those go lower down in branches made specifically for them. You have to create room for variation without creating chaos. There is a pattern called root hardening that is essential at scale. The root management group is where you put the policies that apply to every single thing you own. Because of that, you use it very carefully. You only put the absolute essentials there, like global security baselines that will never change. Everything else lives lower in the tree. That way, when your regulatory requirements shift, and they will, you can update a specific branch without triggering a global crisis. The discipline is this. Every management group needs a documented purpose. Don't just say, this is for platform stuff. Say, this is where we enforce logging for regulated workloads, or this is where we apply least privilege for dev teams. When you get specific about the purpose, the hierarchy explains itself. Teams know exactly where they fit. Policies don't fight each other because they were designed for a specific scope. Once you have the hierarchy sorted, you can finally address the network layer. The connectivity tax, network architecture fundamentals. Your governance structure finally scales. Subscriptions move fast. Management groups keep your policies consistent. But then you hit the next layer, the network, and this is where the hidden costs start to show up. Most organizations default to a centralized model. They want one single egress point, all outbound traffic routes through one firewall, or maybe a pair of them. It's a shared gateway, a single choke point. From a control perspective, this makes perfect sense. You have one place to inspect traffic, one place to enforce your rules, one place to see exactly what is leaving your environment. It gives you unified visibility and total control. It sounds secure, but in reality, it's incredibly expensive. The problem is a pattern called hairpinning. Imagine you have a workload running in East US. It needs to talk to a SaaS service located in North Europe. Under a centralized model, that traffic doesn't just go straight to Europe. Instead, it travels from East US to your central hub, maybe in West US, just to be inspected. Then it finally heads out to North Europe. Your data just traveled west to go east. The path makes no sense. The latency is high, the performance drops, and the costs start to spiral. When you have hundreds of data flows making the same detour, the bill compounds. Azure charges you for data that leaves a region. It doesn't charge for data that stays inside one. Ingress is free, but egress is a line item on your invoice. By forcing traffic through a central hub in a different region, you're creating cross-region transfers that didn't need to happen. You've essentially built a hidden tax into your architecture. The tax is real. Organizations often realize months into a deployment that their egress costs are 5 times higher than they budgeted. The cause is almost always the same: centralized egress. The assumptions about traffic patterns were wrong, and now that connectivity is flowing through a distant hub, the transfer charges are piling up. What actually works is a hybrid model. You need central policy orchestration with distributed enforcement. You define your rules once, what's allowed, what gets logged, what gets inspected, but you enforce those rules at the edge, in every region, in every network. The policy is central, the enforcement is local. Traffic exits exactly where it is, but it still follows the rules you set at the top. This requires a shift in how you think about architecture. You can't rely on one firewall anymore. You need multiple firewalls, one for each region, all running the same rule set. You might use Azure Firewall per region or cloud-native controls like NSGs. The specific tools change, but the principle stays the same. The policy flows down from the center, but the execution happens locally. We call these regional breakout patterns. A workload in East US talks to East US services directly. If it needs to reach something in West US, it can go through a regional firewall or a direct path based on your policy. You aren't funneling it through a central hub for no reason. You're creating natural breakout points where local traffic stays local. Private endpoints and express route are the alternatives to the firewall model. Private endpoints let your Azure workloads reach a SaaS service without ever touching the public internet. The traffic stays on Microsoft's private network. There's no public IP, no standard egress charge, and no need for a firewall to inspect the packet. ExpressRoute does the same thing for your on-premises connection. You pay for the private circuit instead of paying for the data transfer. These aren't free. Private endpoints take time to configure. ExpressRoute requires a contract and an upfront cost. But for high-volume traffic, they are much cheaper than a centralized egress model. They are also more secure because your data never touches the open web. The design principle is simple. Let traffic follow the shortest path unless your policy says otherwise. Don't force detours just because they seem convenient for the networking team. Don't centralize a system that scales better when it's distributed. Network design dictates everything downstream, how teams deploy and what performance they can actually get. If you get the network wrong, every other part of the landing zone suffers. Shared services, the centralization trap. You've fixed the subscription vending. Management groups are working. The network is distributing enforcement. You've finally built a space where teams can move fast. And then they hit the shared services bottleneck. This is where most landing zones fail in the real world. It's not a failure of theory, it's a failure of practice. The logic that works for governance doesn't always work for operations. You can't distribute a logging platform the same way you distribute a firewall rule. You can't put a key vault in one region and expect a team across the world to use it without issues. Shared services have different constraints. When you optimize for centralization without understanding those limits, you haven't solved the problem. You've just moved the bottleneck from the cloud team to the service itself. There is a massive difference between shared and bottlenecked. A shared service is something multiple teams use because building it twice would be a waste of money. Identity, logging, network services. These make sense to share, but shared does not have to mean centralized in one spot. It means coordinated. The old model is the hub and spoke topology. One central hub holds every shared service. The spokes are the individual team subscriptions, everything. Identity, logging, connectivity, routes through that one hub. It sounds efficient because there is only one place to manage. But now, every single workload depends on that hub. If the hub goes down, your workloads can't authenticate. They can't log data. They can't talk to each other. The hub is now a single point of failure for your entire company. As you scale, the burden of managing that hub becomes a nightmare. More traffic, more complexity, and more coordination are required just to make a small change without breaking everything. You need shared logging and identity, but you don't need them in one physical location. You need a central policy for how you log data. You need a central standard for what you monitor. But you can run regional instances of those services. A log analytics workspace in each region, all configured the same way, works much better. Teams log their data locally. Central teams can still run queries across every region. You get the cost savings of a shared model with the resilience of a distributed one. The model that actually works is shared services as a product. Stop looking at these as infrastructure requirements. Start looking at them as products your internal teams consume. That shift changes everything. A product has a roadmap. It has a support model. It has usage metrics and SLOs. When you treat a service like a product, you start measuring whether it's actually helping people or just getting in their way. The metrics are very simple. How long does it take a team to get access to the identity service? If it's hours, you're fine. If it's days, you have a bottleneck. How often does the logging system lag or fail? If it happens once a month, your teams will stop trusting it. What is the delay between an error happening and it showing up in the dashboard? If it takes 2 hours, your developers can't troubleshoot in real time. These aren't infrastructure stats. They are product stats. They tell you if the service is actually usable. Once you look at it this way, the choices become clear. Do you need one central identity service? That depends on the latency your teams can handle. Do you need one central logging workspace? That depends on your data residency rules and query speed. Do you need a hub and spoke network? That depends on your specific security needs and traffic flows. The failure point is always the same. Teams optimize for central control without checking if that control actually works. They build a shared service because it feels right, and then they're surprised when it breaks under the pressure of scale. Performance drops. Maintenance windows start disrupting everyone's work. The fix is to measure everything. Run your shared services like a business. Know your KPIs. Know exactly when you are slowing teams down. When you start looking at the data, you'll realize that shared usually just means bottlenecked because nobody asked if centralization was the right choice to begin with. Once your shared services are running smoothly, the next challenge is scaling this whole mess across multiple regions. Multi-region design. Complexity for complexity's sake. Most organizations eventually reach a point where they make a choice they'll regret. They've built a landing zone that actually works in one region. Subscriptions provisioned fast, policies enforced consistently, shared services work, teams are shipping. Then someone asks, what about multi-region? And the answer is almost always the same. We should probably plan for it. But here's the problem. Most enterprises don't actually need multi-region. They think they do. There's a massive difference. Needing multi-region means you have a business requirement that can't be met any other way. Thinking you need it means it just sounds like a good idea. It sounds resilient. It sounds like what mature organizations do. In reality, the real cost isn't the infrastructure, it's the governance, it's the operational complexity, the data residency constraints. Every new region means new management groups and new policy assignments. You need new subscriptions following the same vending pattern. You need new shared services, identity, logging, monitoring in that specific region, new network boundaries, new naming conventions, new everything. You've just doubled the surface area of your governance model. And the operational complexity scales differently than the servers do. In one region, you have one set of policies to maintain. In 2 regions, you aren't just maintaining twice as much policy, you're maintaining twice as much coordination. Teams in region A have to follow the same standards as teams in region B, but they can't see each other's deployments. They can't quickly check if they're doing things the same way. You've added a coordination tax. Data residency is the constraint most teams underestimate until it's too late. When you move to a second region, you suddenly have to care about exactly where data lives. A workload in East US can log to a workspace in East US without a second thought. But move that to West Europe and you're bound by GDPR. Personal data cannot leave the EU without explicit consent. A multi-region architecture that looks simple in the US becomes a nightmare in Europe. You need separate logging per region, separate backups per region, separate retention policies per region. The question isn't, should we be multi-region? The question is, what would break if we weren't? If the honest answer is nothing, then you don't need it. If the answer is customer compliance or regulatory mandate or latency is killing our users on 3 continents, then you need it. But needing it isn't the same as knowing how to design it. When you do pull the trigger, there are trade-offs. Active-active means both regions handle production traffic all the time. Workloads run in both. Users go to whichever is closer. If one region fails, the other keeps going. It sounds seamless. But active-active means your data consistency requirements explode. You're replicating data across regions in real time. Databases synchronizing, caches invalidating, complexity compounds. Active-passive means one region is primary and the other is standby. If the primary fails, you failover. There's less complexity here, but failover takes time. Minutes at best. During those minutes, your service is degraded. And failover testing is painful. You have to actually failover to know it works, which means you're either disrupting production or paying for an entire second environment just for tests. The cost implications are stark. Cross-region replication is never free. Database replication, backup replication, logging replication, every terabyte you send to a second region is a line item. Failover testing means standing up resources in a second region just to tear them down. Data transfer between regions hits that egress tax we discussed earlier. A simple multi-region design can easily double your Azure bill. Regulatory and compliance drivers are usually the only reasons that actually justify this cost. GDPR forces data residency. PCI requires specific geographic separation. Sovereign cloud regulations require data to stay in a specific country. Those are non-negotiable, but they're also very specific. If you have them, you know it. If you're not sure, you probably don't have them. The model is this. Multi-region is an architectural choice, not a default. If you need it, build for it. But don't build for it because it feels mature. Build for it because your business can't survive without it. Everything else should run in one region until the business proves otherwise. Bicep as infrastructure contract, moving beyond templates. You've now built a landing zone that provisions subscriptions fast. It enforces policy consistently. It networks efficiently. It shares services appropriately. And it doesn't get ambitious about geography. You fix the governance model. The remaining layer is the code itself. And this is where the biggest maintenance mistakes happen. Most organizations treat Bicep files as templates. You write a template for a storage account. You write a template for a virtual network. Someone needs storage. So you copy the template, you modify it for the specific workload, you deploy it. Next request, you repeat the process. Every team starts with a copy. Every team modifies it slightly for their own needs. Within months, you have 50 variations of the same storage account template. Some have encryption enabled, some don't, some have diagnostic settings, some don't. You've got template drift before you've even finished the initial rollout. That's the template mindset. Write it once, copy it many times. Every copy diverges. No 2 copies stay in sync. Maintenance becomes impossible. Security baseline updates become nightmares. You update the encryption standard in the master template, and now you have to hunt down all 50 copies and update them individually if you miss one. There's a non-compliant deployment running in your environment. The contract mindset is different. You write a module, not a template, a module. A module is a reusable component that you version, publish, and consume. You don't copy it, you reference it. You reference a specific version. When you deploy, you're consuming that exact version. When a vulnerability is discovered, you publish a new version. Teams that need the fix upgrade their reference. Teams that don't have time yet stay on the old version consciously. It's a deliberate choice, not an accident of drift. The shift from Bicep files to Bicep modules as versioned products sounds subtle. It's not. It's architectural. It changes how you distribute code, how you maintain it, how you govern it. Azure verified modules are the implementation of this philosophy. AVM modules are Bicep modules that follow a strict standard. They have clear parameters, clear outputs, clear behavior. They are tested, documented, versioned. When you consume an AVM module, you're consuming something that multiple organizations rely on, something that's maintained, something that evolves predictably. For enterprise scale, that predictability is everything. You can't maintain 50 custom templates. You can maintain 2. One for your core platform components, one for workload standard patterns, everything else you consume from a published registry, whether it's AVM modules or your own internal modules. They must be published and versioned like products. Semantic versioning is the discipline that makes this work. You use a major version for breaking changes. Maybe you're removing a parameter that teams relied on. You use a minor version for additive changes. Like adding a new optional parameter, you use a patch version for fixes, like a typo in a default value or a security hardening that doesn't change the interface. Teams see a major version bump, and they know they have work ahead. They see a minor version bump and they know they can adopt it on their own timeline. The cost of forking templates is where this becomes concrete. Someone forks your storage module because they need a slightly different SKU. They modify it, they maintain it separately. 2 years later, you discover a security vulnerability in the encryption config, you fix it in the main module. But their fork still has the vulnerability. Now you're running security patches across 2 code bases, 2 review processes, 2 deployment pipelines. Your governance model has just doubled because nobody enforced the constraint that modules must be consumed, not copied. Version pinning discipline means never referencing latest or main. Never. Those are moving targets. You reference 1.3.2, a specific version. When you're ready to upgrade to 1.4.0, you make that decision explicitly. It's a pull request. It gets reviewed, it gets tested, then you merge it. Now you're on the new version and you stay there until you decide to move again. No surprises. No automatic upgrades breaking things in production. No, the template changed and now everything fails. That discipline scales governance, because governance isn't enforcement anymore. It's versioning, it's publishing. It's knowing that every deployment is using a known, tested version of the module. Not a drift-infected copy, not a moving target. A contract, a versioned, documented, published contract. Once modules become contracts, governance becomes measurable. Module composition patterns, building reusable infrastructure. You understand modules as contracts, but how do you design those contracts so they actually work at scale? The first instinct is usually to build comprehensive modules. One single module that deploys a complete workload. Compute, storage, networking, identity, monitoring. It's all in one place. It feels efficient because you have one version and one reference. And everything stays synchronized. But in reality, it fails the moment you hit real complexity, because a module that does everything is just a God module. It ends up with 50 parameters, half of them are optional, and nobody can remember which combinations actually work together. When you need to update one small piece like a monitoring setting, you have to bump the version for the entire stack. Teams that don't even care about monitoring now have to decide if they should upgrade or stay on an old unsupported version. You've created artificial coupling where none needed to exist. The model that actually scales is layered composition. Think of it in 3 tiers. The bottom tier is primitives. A primitive module is a single resource or a very tight set of resources, like a storage account, a virtual network, or a managed identity. These are small and focused. They do one thing well. They have minimal parameters, but very rich outputs. Everything downstream might need to know about them, so you expose the resource IDs, the principal IDs, and the endpoints. The middle tier is patterns. A pattern module composes those primitives into a solution. A web app pattern might pull together storage, compute, and identity. But it isn't just a big file of code. It references the primitive modules and wires their outputs together. Because you're building on proven primitives, the pattern module stays simple. You only expose the parameters that actually matter for that specific pattern. The top tier is solutions. A solution module is what a team actually consumes. Maybe it's a microservice landing zone that uses the web app pattern and adds networking and security. A developer says, I need a microservice environment. They consume the solution. They don't need to know how the primitives or patterns work internally. They provide a workload name and some basic config, and they get a coherent deployment. This layering solves a massive problem. When a security flaw is found in how your storage handles encryption, you fix it once in the primitive module. That fix automatically flows up through every pattern and every solution. One fix, total scale. But this is where most teams fail. Parameter design. The instinct is to make the module maximally flexible by exposing every possible option. But maximum flexibility is just maximum complexity. A module with 30 parameters is a module nobody understands. People end up guessing which combinations are correct, and they usually get it wrong. The balance is simple. Parameterize what actually varies. Everything else becomes an opinionated default. A storage module should ask for the account name, the location, and the replication strategy. Those change based on the workload, but that same module should default to encryption enabled and firewalls turned on. Those are baseline standards. They aren't options, they're just how you do things. Then you have outputs. Outputs are your public interface. Most modules are under-designed here. A storage module that only gives you the account name is useless to a downstream resource. You need the account ID, the blob endpoint, and the principal ID for identity. The module that created the resource already knows these values. Expose them. Don't make downstream modules try to calculate them again. There is also a specific approach called the shared variable file pattern. Sometimes you have complex config, like a network security group with dozens of rules. You don't want all of that cluttering up your module parameters. Instead, you store that data in a JSON file. The module loads the file and uses it. The team updates the JSON, not the module code. The configuration stays external and the module stays clean. The guiding principle is this: a module should be usable by someone who has no idea how it works inside. If a developer can't use your module in 5 minutes without reading your source code, you've over-designed it. Once these patterns are in place, you need versioning discipline to keep it all from falling apart. version control and release discipline. Version control isn't just a storage locker for code. It's the mechanism that prevents drift. It's what keeps your infrastructure consistent across different teams and different years. Without it, you're just managing hundreds of manual variations. But here's the problem. Version control for Bicep is not the same as version control for application code. With an app, you version the whole code base together. One repo, one release. That works because the app is a single unit that you deploy all at once. Infrastructure is different. A platform team might own the network. A security team owns the policies. A database team owns the storage patterns. They are all moving at different speeds. If you lock them into one repository with one release cadence, you create massive overhead. The network team can't ship a critical fix because they're stuck waiting for the security team to finish a new feature. The shift you need to make is separating code repositories from configuration repositories. The code repo holds your modules, your primitives, and your solutions. This is where the engineers work and where you track every logic change. The configuration repo holds the actual values, like the biceparam files. This is where the application teams live. This is where you track exactly which version of a module is running in production. This separation solves the scaling issue. 5 different teams can own 5 separate module repositories. The network team and the identity team maintain their own code and version it independently. The configuration repo acts as the coordinator. It points to specific versions of those modules. When the network team releases version 2.1, the configuration doesn't just automatically update. Someone has to review the change. They test it in a sandbox, they approve it. Then they update the reference to 2.1. That is a deliberate choice, not an accident. This is also where you use CI/CD gates to enforce quality. Before any change hits the main branch, it has to pass a validation check. For Bicep, that means a what-if deployment. You compile the code and run what-if against a test environment to see exactly what would happen. If the changes look right, the gate opens. If the tool shows a resource getting deleted or a breaking change you didn't expect, the gate stays shut. The pull request can't merge until the logic is fixed. To handle the overhead, use path filters and per-module pipelines. If you have 10 modules in one repo and you change one, you shouldn't trigger 10 releases. You only want to run the pipeline for the specific folder that changed. Tools like Azure Pipelines or GitHub Actions handle this easily. When the network folder changes, you run the network pipeline. No unnecessary versions and no artificial coupling. For the actual lifecycle, Azure uses deployment stacks. A stack is a managed unit that knows exactly which resources belong to it. When you update a template, the stack knows what to add, what to modify, and what to clean up. It can even enforce deny assignments so people can't manually delete things. This is vital for shared services. You don't want a random admin deleting a central logging resource because they thought it was leftover junk. Then there are breaking changes. When you remove a parameter or change how a module behaves, you bump the major version. That's the signal to every consuming team that they have work to do. If 50 teams are using your module, a breaking change means 50 updates that need to be coordinated. You have to plan for that. Communicate it early. Provide a clear migration path and keep the old documentation live as long as teams need it. The discipline is simple. Every version is immutable. Once you publish version 1.3, that code never changes. If you find a bug, you publish 1.3.1. When a team is using 1.3 and hits a bug, they know they aren't alone. They can find the known issues and compare notes with others. That immutability is what creates predictability. And that predictability is what allows a platform to evolve without breaking everything in its path. Teams know what's changing, when it's changing, and exactly what they need to do to keep up. The subscription vending machine, automating onboarding. Subscription vending is where governance meets agility. It is the operational hinge that everything else depends on. Everything you have built so far. The management group hierarchy, the policy assignments, and the baseline configurations only matters if teams can actually create subscriptions and get to a usable state without waiting. The old model was built on friction. A team needs a new environment, so they fill out a form and answer questions about workload type, team size, and compliance requirements. They explain if it needs to talk to on-premises systems or if it faces the public internet. In most organizations, that form is a 20-page questionnaire that leads to a manual ticket which sits in a ServiceNow queue while it waits for a human to review it. But in reality, that assumption is broken. Work doesn't start with a ticket, it starts with context. The new model uses a simple form with 5 or maybe 10 fields, which provides just enough context to make automated decisions. When that form is submitted, it triggers a Bicep deployment, not a request, a deployment. That deployment handles everything by creating the subscription in the right management group and assigning the correct policies based on compliance needs. It configures RBAC so the team has ownership immediately, and it sets up logging, monitoring, and a virtual network with the right address space. By the time the form submission completes, the subscription is ready. Not days away, not weeks away, ready. The speed difference is profound. Manual requests take weeks because they require constant coordination, starting when a cloud operations person reviews the ticket and asks clarifying questions. They coordinate with security to check policies and networking to ensure the address space does not conflict, and then they manually click through the portal to create resources. 2 weeks later, the team finally has something they can work with. Automated vending takes minutes. The form validates the data immediately and the Bicep deployment runs because the standard decisions are already encoded. No human judgment is needed during the process because that judgment was already applied once in the code itself. If the deployment fails, the problem is usually simple and fixable, like an invalid address space or a duplicate name. It is never a case of needing to talk to 3 more teams before getting an approval. Using Bicep to automate this requires discipline, and the vending machine must be flexible enough to handle different needs. A development environment requires different configurations than a production environment, just as a machine learning workload needs different resources than a simple web application. The Bicep code uses parameters for workload type, environment classification, and compliance tiers to make these decisions. For a development environment, the machine creates a single subscription with minimal policies and looser RBAC so teams can experiment. When it handles production, it creates subscriptions in a different branch of the hierarchy with stricter policies, restrictive RBAC, and mandatory logging. For machine learning, it provisions specific compute resources like GPU quotas and higher storage limits that would not make sense for a web app. The self-service portal is where usability matters most. The form cannot be hidden in an internal wiki 3 levels deep, so it needs to be discoverable, simple, and capable of providing real feedback. If a submission fails, teams need to know why and how to fix it right then. If the deployment is taking time, they need visibility into the progress. A portal that just accepts a form and disappears is a portal that gets abandoned, and teams will stop using it and go back to manual tickets or, even worse, shadow IT. The tension lies in balancing automation with necessary guardrails. You want to automate as much as possible, but some decisions still need a human eye. Maybe a team is requesting an unusually large number of subscriptions, or a workload has compliance needs that do not map to your standard categories. These cases need an escalation path, not a rejection, not a you can't do this, a path. An approver reviews the request and makes a decision, and that decision is documented. If you see the same type of request repeatedly, you update the vending machine to handle it automatically next time, rather than keeping the same problem escalated. The cost of not automating is staggering. Organizations that still use manual ticket-based provisioning spend massive amounts on operational overhead. Cloud teams get buried in tickets while security teams perform the same compliance review 50 times instead of encoding it once. Finance teams end up tracking manual chargebacks because subscriptions were not tagged consistently at the start. Shadow IT grows because the official path was so slow that teams felt they had to create their own way forward. Once subscription vending is working, teams can move fast within the governance structure. Fast provisioning only works if the governance is sound, and the vending machine is fast because the rules it encodes are trusted by the organization. Teams do not have to wait, and they do not have to wonder if their environment is compliant. It was created by the machine, it is compliant by design. Policy as code. Guardrails versus gates. Policy as code means different things to different people. Most teams think it just means writing policies in code instead of clicking through the portal, but the distinction that actually matters is the difference between guardrails and gates. A guardrail is a boundary. It is a safe edge that lets you move freely as long as you stay within the lines. A guardrail keeps you from falling off a cliff, but it does not tell you which direction to walk. You go where you want. You are just protected from the worst-case outcomes. Gates are different. Gates block you. You hit a policy gate and your deployment stops until someone or something opens it. Gates are explicit blocks. They are rejections. Most organizations implement their first policies as gates, where they deny this and they deny that. A deny policy on public IP addresses means you cannot create a VM with a public IP, so the deployment fails, the gate closes, and you are stuck. The policy achieved its goal of stopping public IPs, but it also created a secondary problem. The team that actually needed that IP for a testing scenario or a temporary debugging session now has to file an exception request. That means a ticket. That means waiting. The team gets frustrated and finds a workaround, perhaps by creating the resource in a personal subscription or using a different tool entirely. The gate did not actually prevent the behavior. It just moved the behavior outside of your control. Guardrails work differently. Instead of denying public IPs, you assign a policy that audits them. So every public IP deployment is logged and flagged. You can see who is creating them and why, but the deployment still succeeds. The team gets what they need without an exception request or a long wait, and you have gained visibility without creating friction. The rollout strategy that actually works is audit first, then enforce. You start with every policy in audit mode. Not deny, Audit. The policy runs and flags violations, but it does not block any deployments. You let this run for several weeks while you collect data. You see which policies are actually triggering and which ones are just edge cases. This is when you involve the teams and ask them why certain deployments do not meet the baseline. The teams explain their context, which might include legitimate needs, simple mistakes, or workarounds for missing capabilities in the platform. Then you move to enforcement, but only for the policies where you have validated the impact. You only turn on deny once you have a clear exception process and you have ensured the governed path is faster than the ungoverned one. Rushing straight to deny policies is how you end up with teams circumventing your governance entirely. Deny policies have a hidden cost that organizations rarely measure. The cost is not in the IT budget, it is in productivity. When a team hits a deny policy, they have two choices. They can file an exception and wait, or they can find a workaround. The workaround costs real time and real money. A team that spends 2 hours bypassing a policy because an official exception would take 3 days has just lost 2 hours of work. When you multiply that across an entire organization and every policy you have in place, you find the actual cost of your governance. Policy compliance metrics tell a story if you know how to read them. A compliance rate of 98% sounds good, but it depends entirely on what you are measuring. If you are checking if resources have the right tags, 98% is probably fine. But if you are measuring whether virtual machines have encryption enabled, that 2% gap means you have unencrypted data sitting in your environment. The metric matters, the threshold matters, and the trend matters more than the absolute number. If compliance is dropping month over month, something is wrong with the system. Maybe the policies are getting too strict, or maybe teams are being pushed toward workarounds to get their jobs done. This is a signal that you need to revisit the policy set. Exception management is where most organizations fail silently. A team needs an exception to a deny policy, so they file a request. But because no formal process exists, it goes to an email chain, someone approves it somewhere, but there is no record and no tracking. A month later, nobody remembers what was approved or why it was allowed, and you have created a governance process that is essentially invisible. The fix is structure. You must make exceptions trackable and time-bound. If you approve an exception for 6 months, it should expire unless it is explicitly renewed. If the same exception keeps getting renewed over and over, that is a signal that the policy itself probably needs to change. You have identified a gap between the intent of the policy and the reality of the work. Policies only work when they are paired with usable alternatives. Governance succeeds when the governed path is genuinely faster than the shadow path. Identity and access at scale. Identity is the control plane for everything else. Not the network, not the policies, identity. Because every deployment, every configuration change, and every access request flows through identity. When identity is right, governance is enforced automatically. When identity is wrong, governance is theater. You end up with policies nobody can trigger. You have resources nobody can reach. You have audits showing compliance that's meaningless. Because the people auditing don't even have access to the systems they're checking. The first mistake organizations make is treating identity as infrastructure. They deploy Microsoft Entra ID and call it done. But identity isn't infrastructure, it's governance itself. Every permission you grant is a governance decision. Every role assignment is a control. Every conditional access rule shapes what teams can do, and when they can do it. Managed identities versus service principles is where this gets concrete. A managed identity is what you use when a resource needs to authenticate without a human involved. For example, a VM needs to pull a secret from Key Vault. It gets a managed identity. The vault trusts that identity. The VM authenticates without passwords. No human has to manage credentials. No credentials get stolen because they're not sitting in a config file. They don't exist outside Azure. That's the model. That's how identity at scale works. Service principles are the alternative. They're identities that represent applications, but they have passwords or certificates. Someone has to create them. Someone has to manage the credentials. Someone has to rotate them before they expire. Service principles are still necessary in some cases. External systems need to authenticate to Azure and they can't use managed identities, so they use service principles. But for everything internal to Azure, managed identities are the answer because they remove the credential management problem. And credential management at scale is where most organizations fail. Federated credentials solve the CI/CD problem. Your GitHub Actions workflow needs to deploy infrastructure to Azure. It can't use a managed identity because GitHub is external to Azure. Historically, you'd create a service principal, generate credentials, store them in GitHub secrets. That works, but credentials in GitHub secrets are a problem waiting to happen. They get rotated on a schedule. They expire. Someone has to remember to rotate them before they expire. And leaked GitHub secrets in commit history are a real risk. Federated credentials let you say, GitHub Actions can authenticate to Azure without passwords. The GitHub workflow has an identity. Azure trusts that identity because GitHub cryptographically proves it. No credentials, no secrets, no expiration. The workflow authenticates. It gets a token. It deploys. That token is short-lived. It's used once. It can't be stolen because it exists only for the moment it's used. That's the model. That's how you do it at scale. RBAC inheritance through the hierarchy is where governance becomes operational. You designed a management group hierarchy. Each level has policies. But RBAC is part of that hierarchy too. You assign a role at the root management group level and it cascades down to every child, every subscription, every resource group, every resource. Designed for least privilege at the hierarchy level. And every subscription you create gets least privilege by default. You don't have to manually configure it on each one. The discipline is never assign roles at the resource level if you can assign them at a higher level. Assign them at the right level. A team that manages identity components gets assigned roles on the identity management group. A team that manages networks gets assigned roles on the networking management group. Not on individual resources, not on individual subscriptions. On the management group where their scope applies, everything underneath inherits the correct level of access. Break glass accounts are the emergency access pattern. Something is broken. Your automation is failing. You need to fix it now. You need to access resources, but your normal access controls are preventing it. Break glass accounts bypass those controls. They're restricted. They're audited heavily. Access requires approval from multiple people. But they exist. They're prepared ahead of time. You test them quarterly so you know they work when you actually need them. Then you document what happened, why you needed to use them, what changed to prevent needing them again. Conditional access policies shape deployment workflows in ways teams don't always understand. A team's developers can access Azure from the office, but Azure detects they're accessing from a coffee shop and blocks them. That's conditional access. It's appropriate in some contexts, but it's also friction. Design the access policy you need, but measure the friction it creates. When the friction outweighs the risk, change the policy. Identity is foundational. Every other control depends on it working correctly. Observability as a governance mechanism. Here's what nobody tells you about logging. It's not about troubleshooting. Not primarily. Yes, you need logs to figure out why something failed at 3 a.m. But that's the convenience benefit. The actual purpose is different. Logging is how governance proves it happened. It's the audit trail. It's the insurance policy. It's the mechanism that turns governance from intention to evidence. When you make a policy decision, this resource must be encrypted, this identity must use multi-factor authentication, this deployment must come from an approved pipeline. Logging is what proves the policy is actually being followed. Without logging, you have a policy nobody can verify. You're trusting based on assumption. With logging, you have records. You can prove compliance, you can prove violations, you can prove who did what and when. Most organizations think about logging wrong. They think it's about collecting everything, dump all logs into one central place, make it available to whoever needs it. That sounds reasonable. In practice, it becomes a governance nightmare. You've got years of logs, terabytes of data, no organization, no structure. Searching for a specific event takes hours. The volume of data becomes a cost problem. You're storing logs you'll never look at. You're paying for retention policies that are too long or too short. You're not actually getting value from the logging infrastructure. Centralized log analytics workspaces create architectural implications that matter. If you have one workspace for your entire organization, every workload in every region and environment is logging to the same place. That's a single point of failure for observability. If the workspace is unavailable, you have no visibility into what's happening. It's also a query performance problem. Queries across terabytes of data slow down. It's a cost problem. Cross-region data transfer charges if you're replicating logs from multiple regions to a central location. It's an access control problem. If you have one workspace, you need to manage access centrally. A team in one region can see logs from another region. That might be fine. It might not be, depending on your compliance requirements. The architecture that works is regional logging with central visibility. Each region has its own log analytics workspace. Teams log locally. But there's a central workspace that aggregates the important stuff. Not everything, just the signals that matter for governance. Security events, policy violations, compliance audits, identity access changes, deployment activities. The high signal data flows to the center. Low signal data stays local. You get visibility without the volume problem. Diagnostic settings are the governance requirement that most organizations enforce last, or never. You should enforce them first. Every resource should have diagnostic settings configured. That means every resource is logging automatically. Not optional, not configurable by the team deploying the resource. Mandatory, built into the resource as it's created. The vending machine that creates subscriptions, it configures diagnostic settings on the resources in those subscriptions. The module that creates a storage account, it enables diagnostics on that storage account. You don't ask teams whether they want logging. Logging is how you know what's happening. The cost implications of centralized logging across regions is where the economic model matters. Data transfer between regions costs money. If you're collecting logs from East US and replicating them to West US for central analysis, you're paying for that data transfer. The more regions you have, the more the transfer costs. Design for this. Use regional workspaces as the primary repository. Replicate only what's essential to the central workspace. Or use a cheaper tier for long-term retention and a hotter tier for recent data. The point is, know the cost model. Don't discover 6 months in that your logging infrastructure is costing more than your compute infrastructure. Using telemetry to detect drift and non-compliance is where observability becomes governance automation. You're not just collecting logs, you're analyzing them. A deployment happens. You query the logs. Did it follow the security baseline? Was encryption enabled? Were mandatory tags applied? The logs tell you. If compliance is drifting, more and more resources without required tags, more deployments missing security configurations, the logs show the trend. You catch it early instead of discovering it in an audit 6 months later. The difference between monitoring and observability is this. Monitoring tells you if something is broken. Observability tells you why it's broken. Monitoring is alerting when CPU hits 90%. Observability is showing you the request patterns and resource allocation that caused CPU to hit 90%. One tells you there's a problem. The other explains what caused it. Both matter. But observability is what makes governance operational. You can see not just that a resource exists, but how it was created, who created it, whether it's being used, whether it's compliant, and what it's costing. With observability in place, cost governance becomes measurable. Cost governance and FinOps integration. Cost is a governance lever. Most organizations treat it as a finance problem where the CFO owns the budget and the finance team manages the spreadsheets. In that old model, IT just pays the bill and moves on. That model is broken. In reality, cost is how you enforce governance at scale because teams don't change their behavior for a policy document. They change when they see the bill. When teams are accountable for what they spend, visibility forces them to justify their choices. That's where the shift happens. Your tagging strategy is the foundation here. It's non-negotiable. Every single resource must have tags, and it can't be optional. We can't rely on teams to remember to tag things. It has to be built in. The vending machine that creates your subscriptions shouldn't ask if a team wants tags. It should just apply them. Owner tags, cost center tags, environment and application tags. These tags need to flow through to every resource created in that subscription. They're inherited, they're consistent, and they are the foundation for everything you do downstream. Without tagging discipline, your cost reports are useless. You might get a bill for $50,000 in compute costs, but you won't know which team caused it. You won't know the workload or the environment because you can't see the data, you can't charge them back or optimize the spend. You can't even find the resource to see if it's actually running or just abandoned. Tagging solves this by tracing every dollar back to the team that created the resource. This allows you to measure if they're actually optimizing or just letting expensive resources run unused. The real behavior change happens when you move from showback to chargeback. Showback is just informational. You show a team they spent $10,000 last month, but they don't pay it directly. It's just a corporate cost, so most teams don't change a thing. Chargeback is different. Chargeback means the team is actually charged and their budget gets debited. Now they have to justify that expense to their manager. They have to explain why a GPU cluster is running in dev when nobody is using it. It changes behavior because it's their money, or at least their budget. It's the difference between being told you're spending a lot and seeing your own allocation disappear. One changes behavior, the other doesn't. Budget alerts and quotas are just policy mechanisms wearing a different hat. You set a monthly budget, and when a team hits 80%, they get an alert. When they hit 100%, their ability to create new resources gets restricted. We don't block them entirely. We just add friction. If they truly need to deploy, they have to actively override the quota and acknowledge they are going over budget. That moment of friction causes them to stop and think. Most of the time, they don't override the limit. They optimize instead. Reserved instances and savings plans are where things get complex in multi-team environments. They're much cheaper. A 3-year commitment can be half the price of on-demand, but it's also inflexible. You're locked into specific sizes and regions. If a team changes their workload, that reservation doesn't move with them. Now you have one team paying full price while another team's reservation sits empty because it's locked to the wrong group. The model that actually works is centralized reservation buying. The platform team buys capacity based on the total aggregate demand of the whole company. Production compute gets reserved, dev gets a smaller slice, and the savings are distributed back to teams based on their usage. This lets teams get the lower costs without needing to predict their exact needs 3 years in advance. The platform absorbs that risk. You'll see the connectivity tax show up in these reports too. This is where network architecture decisions finally become visible to the business. A team might put a VM in East US but route all traffic through a West US firewall. Suddenly they see a bill for $2,000 in data transfer. When they ask why, you show them the network path. They see the flaw, they move the VM or fix the firewall, and the cost drops. Tag-based billing makes invisible architectural flaws impossible to hide. And once you have cost visibility, it enables the next layer. Security. Security baselines and compliance codification. Security baselines aren't something you design once and forget. They are living documents. Threats change. Regulations shift, technology evolves. A baseline from 3 years ago might say TLS 1.2 is fine, but today that's a vulnerability. Your baseline should now require TLS 1.3 as a minimum. But if you've coded that baseline into your infrastructure, updating it means updating every resource you've ever deployed. The big question is, how do you evolve these baselines without breaking everything? The answer is codification. Encryption, private endpoints, and network isolation shouldn't be manual steps. They should be the defaults. These are baked into the modules that create your resources. Your storage module doesn't ask if you want encryption. It's just enabled by default. Your database module is HTTPS only, with no exceptions allowed. Your networking module uses private endpoints for connectivity and blocks public access. This matters because security through defaults is the only way to scale. When a team deploys a storage account, it's encrypted because the module made it that way. The decision was made once during the design phase. The team can't accidentally disable it during deployment. This is where Microsoft Defender for Cloud makes your design observable. Defender scans for misconfigurations like open ports or weak authentication. When it finds a problem, you fix it, but that fix has to flow back into your baseline. If one resource has a hole in it, it's probably because your baseline allowed it to happen. When you update the baseline, new resources get the fix by default. Existing resources start showing violations, which gives you the visibility and accountability you need to clean them up. Compliance frameworks are where security becomes an operational policy, whether it's CIS benchmarks, NIST, or PCI DSS. These aren't just suggestions. If you're in finance or healthcare, these are mandatory. But these frameworks are incredibly detailed. NIST 853 has hundreds of controls, and you can't manually audit every resource against all of them. It's impossible at scale. So you encode those controls directly into Bicep. If a framework says all data in transit must be encrypted, that becomes your policy and your module default. It becomes a validation gate. If someone tries to deploy something that isn't encrypted, the gate fails and the deployment stops. The control is enforced automatically. When an auditor asks how you ensure encryption, you don't show them a spreadsheet. You show them the Bicep code. You show them the module, the default settings, and the policy that validates it. You've turned compliance from a mountain of paperwork into a few lines of code. This brings us to the economic argument, the cost of remediation versus the cost of prevention. You can deploy a storage account without encryption and try to fix it later. But remediation means change. It means testing, potential downtime, and coordinating with the teams using that resource. It's expensive and slow. Prevention is much cheaper. If you deploy with encryption enabled from day one, there is no remediation needed and no risk to the business. Remediation costs scale terribly. One non-compliant resource takes hours to fix, but 100 of them can take weeks of manual effort. Eventually, the backlog grows so large that organizations just give up. They accept the risk because fixing it is too expensive. But if you had prevented the issue at the start, the cost would have been zero. Audit readiness has to be a design requirement, not an afterthought. Most organizations treat audits like a massive yearly event where everyone scrambles to find evidence. They hope the documentation is good enough and that nothing has changed since the last check. That is the wrong model. Audit readiness should be continuous. Your logging should be so complete that you can answer any question in minutes. Your Bicep modules should be so standardized that you can prove every control is applied every time. Your policy assignments should be visible so you can show exactly which controls are active. When you design for continuous readiness, the actual audit becomes a formality. The auditors show up, you pull a report, and you show them the code and the posture. Everything is documented and current. There's no scrambling and no stress. You're ready, because you've been audit ready the entire time. Security and compliance only work when they are automated. The shadow it signal, what it's actually telling you. Shadow it isn't what most organizations think it is. It isn't a security failure. It isn't recklessness. It isn't insubordination. It's a diagnostic signal. Think of it as the infrastructure equivalent of a check engine light. When shadow it appears, it means something in your governance model is broken. The system isn't working for the people who actually use it. The teams aren't the problem. The model is. The data shows this pattern over and over again. When governance becomes too slow or too rigid, shadow IT adoption spikes. Teams stop trying to work within the system because the friction is just too high. Instead, they find a way around it. You see personal Azure subscriptions showing up on corporate credit cards. You see AWS accounts opened without a single approval. You see SaaS platforms being used that don't require IT to get involved at all. These teams aren't trying to be difficult. They're being rational. They are solving the problem right in front of them. And because the governed path costs too much time, the shadow path becomes the only viable option. The numbers here are staggering. The average cost of a shadow IT incident is $4.2 million. That sounds like an abstract figure until you look at what's actually happening behind the scenes. A team starts using an unsanctioned SaaS platform. Your customer data begins flowing through it without your knowledge, which means it's operating without your encryption or your backups. Then a breach happens. Suddenly, that data is exposed to the world. You're looking at notification costs, remediation fees, and massive regulatory fines. Then comes the investigation, the damage to your reputation, and the customers who leave and never come back. That $4.2 million is very real. But here's the distinction. That cost doesn't exist because the teams are malicious. It exists because they operated outside your visibility. If that team had requested the platform through official channels, you could have evaluated it. You would have either approved it with the right security controls or pointed them toward an alternative that already solved the problem. The cost of shadow IT is really just the price of having systems you can't see. The logic behind personal subscriptions is exactly the same. A team needs to test a new architecture pattern or a different database technology for a client proof of concept. They need to move fast. The official process takes 3 weeks. The evaluation takes another 2. The final approval takes 1 more. That is a full month of waiting for a client who needs an answer in 14 days. So they open a personal Azure account, they deploy the code, show the client, and get the answer they needed. They weren't trying to hide anything from you. They were just trying to deliver their work on time. Adopting external SaaS is driven by that same root cause. Maybe your data warehouse is slow, and the analytics team is tired of waiting weeks for queries to finish. They find a faster alternative that solves their problem immediately. Now, your customer data is living on an external server. They didn't want to expose the data, but the official warehouse wasn't doing its job. There is a direct link between rigid governance and shadow IT. Organizations that lean heavily on deny policies see these spikes. Organizations that take months to provision a single subscription see these spikes. It isn't a coincidence. It's causal. Rigidity drives avoidance. You find what's happening by looking at the discovery patterns. Expense reports show cloud charges on personal accounts. Network monitoring picks up unexpected traffic to external platforms. Identity logs show people logging into services that aren't in your catalog. You listen, you observe, you discover. And when you find these things, the question shouldn't be, how do we shut this down? The question should be, why are they using this and what is missing from our official offering? The real strategic shift is converting shadow IT into governed IT instead of just blocking it. When you see a team using an external data warehouse, you ask them what problem it solves. Is it about the speed? Is it a specific feature? Is it the cost? Once you understand that need, you have 2 choices. You either build that capability into your official warehouse, or you adopt the external tool officially. You integrate it, you secure it, and you govern it. The team gets the solution they need. You get the visibility you require. The shadow IT becomes official, and the problem is actually solved. This takes organizational maturity. It takes confidence. It requires you to admit that your current system isn't meeting every need. But the organizations that do this turn a security liability into a competitive advantage. Teams get what they need to work, governance actually improves, and shadow IT shrinks. Not because you blocked it, but because you finally addressed the demand. The platform, engineering model, enablement over gatekeeping, recognizing shadow. IT as feedback tells you what is broken, but fixing it requires a structural shift. Most organizations still treat infrastructure teams like gatekeepers. The infrastructure sits in the middle while applications come to them with requests. The team evaluates, then they approve or deny. In this model, infrastructure controls the pace. Infrastructure is the bottleneck. Platform engineering flips that dynamic on its head. Infrastructure becomes a product team where the product is the platform itself. The customers are the application teams. In this world, the success metric isn't how much did we control, it's how much did we enable. The platform team doesn't spend its day approving requests. It builds products that other teams consume. It doesn't slow people down. It speeds them up. This is a cultural shift more than a technical one. When you are gatekeeping, the model is based on permission. Do you have permission to create a resource? Do you have permission to deploy? Every single action requires a green light from someone else. When infrastructure is a product, the model is based on capability. Can you use this feature? Is it available to you? Can you deploy using this template? This distinction is huge because permission-based models create friction even when the answer is yes. A team asks for permission, and then they wait. Eventually, permission is granted and they proceed. That process is serial. It's slow. Capability-based models are different. The capability already exists, so the teams just use it. There is no waiting and no asking. It's parallel. It's fast. The golden path is what makes this work. You look at the workflows that happen over and over again, like deploying a microservice or standing up a database environment. For each of these, you build a golden path. This is an opinionated, tested, and secure way to get the job done. It's a template or a self-service offering that just works. The golden path isn't the only way to do things. Teams can deviate if they really need to, but the golden path is intentionally easier. It's faster, it's better documented, and it works for 80% of use cases. Teams use it because it's convenient, not because they are forced to. They use it because it solves their problem without the headache. Self-service templates are how teams actually interact with the platform. But a portal that requires 10 clicks to find a template is useless. Teams won't use it, they'll just go back to building their own tools. The platform needs to be discoverable where the work is already happening. It should be in their IDE, their GitHub organization, or their deployment pipeline. It needs to be right where they are already solving problems. Documentation is also more important than most people realize. A template without examples is a template that nobody will ever touch. But a template with clear examples and copy-paste parameter files becomes a natural part of the workflow. Eventually, teams don't even think about the fact that they're using the platform. They're just solving the problem. When the platform disappears, you know you've succeeded. Developer experience is the metric that separates platform thinking from the old way of doing things. In the old model, you only measured if policies were enforced. You looked at the compliance rate and checked if resources had the right settings. That's a fine metric, but it doesn't tell you if the experience was actually good. A team could follow every single policy while being completely miserable. The infrastructure succeeded, but the developer experience failed. In platform thinking, you measure how easy it is to do the right thing. How long does it take a team to deploy their first resource? How many authentication prompts do they have to click through? Do the error messages actually explain what went wrong? When a team needs help, how fast do they get it? These are the metrics that matter. They tell you whether teams will actually use your platform or if they're going to start building their own. Feedback loops are how these platforms stay relevant. The platform team can't live in a vacuum. They have to listen. They need to see which templates are used most and which ones are being abandoned. They watch the support channels to see which problems keep coming up. They look for the requests that don't fit any existing template. That is the signal. That signal tells you where the platform needs to evolve. Maybe you need a new template, or maybe an existing one needs to be completely redesigned. Using telemetry to improve the platform turns governance from something static into something adaptive. If you see teams struggling with network configurations, you realize the template has too many parameters. So you simplify it. You create sensible defaults for 90% of cases. The struggle goes down, the platform evolves, and teams start shipping faster. That is the flywheel. The cost of a bad platform experience is real. If teams can't figure out how to use what you've built, they will build their own. You'll see that shadow IT signal again. This means platform thinking isn't just a theory. It's a practical necessity. It is the difference between teams using your infrastructure and teams working around it. Success isn't about compliance or control anymore. It's about velocity. It's about satisfaction. It's about adoption. Success is when teams ship faster because the platform finally got out of the way. Multi-tenant governance, Bicep across organizational boundaries. Platform thinking works for a single tenant, but most large organizations don't stop there. They have many. Multiple business units, multiple geographic regions, or multiple customer organizations if you're a service provider. Each has its own Azure tenant, each has its own governance rules, and yet, each still needs access to your shared infrastructure patterns. The moment you cross a tenant boundary, everything gets harder. Not because the technology changes, Azure works the same way. The hardship comes from the organizational walls. Tenants are trust boundaries. One tenant's security team doesn't control the other. One identity system doesn't automatically trust the next. Permissions don't flow, and access doesn't cascade. You have to build every bridge across that boundary explicitly. Cross-tenant module consumption sounds simple in theory. Tenant A builds the modules, and tenant B consumes them, but in practice it breaks because of how Azure's registry authentication works. Bicep modules live in an Azure Container Registry, and to pull a module, you need permissions on that specific registry. This means the owner has to grant credentials to people in another tenant, or you have to configure complex cross-tenant authentication. Both options have friction. Neither is easy. The pattern most organizations actually use is registry per tenant. Tenant A publishes to its registry, and tenant B publishes to its own. They maintain their own copies. They stay in sync through process discipline and automation. When tenant A releases a new version, tenant B pulls it into their own registry after testing or a manual review. This redundancy feels inefficient, because it is. But the autonomy feels right. Each tenant controls its own registry and manages its own credentials. There is no cross-tenant authentication to debug. The trade-off is obvious. Registry per tenant is operationally cleaner, but it's also organizationally fractured. If you have 5 tenants, you have 5 separate repositories and 5 separate release cycles. When a security flaw is found in your storage module, you have to fix it 5 times. You have to coordinate 5 different releases. That is the tax you pay for autonomy. The alternative is a central registry shared across every tenant, one source of truth, and one place to update a code block. Updates flow to everyone automatically, but shared registries require shared authentication and shared access control. It requires deep trust. It requires one security team to believe the other team's practices are actually sound. Azure Lighthouse helps solve part of this. Lighthouse lets you set up delegated administration across those boundaries. Tenant A can give tenant B access to specific resources without sharing credentials or creating new identities. It's clean. But Lighthouse is for managing resources, not for distributing modules. You can use it to deploy modules from a central tenant into a customer tenant, but that's an orchestration model. The customer isn't consuming the module. The central team is just deploying it on their behalf. Version pinning becomes critical across these boundaries because the stakes are higher. When tenant A updates a module, tenant B doesn't get it immediately. They have to decide when to upgrade. If tenant A releases a breaking change and tenant B stays put, the modules still reference the old version. It works. But now you have divergence. One team is on version 2.0 while the other is on 1.3. They are running different infrastructure with different bugs and different features. The discipline is simple. You must treat cross-tenant modules like public open source code. You pin versions explicitly. You read the release notes. You test before you touch anything. You upgrade on your own schedule. not the publishers. It is more work than single-tenant consumption, but it's the only way to maintain governance across boundaries. The upstream-first model avoids forking. You consume from the central repository instead of copying and modifying the code. You don't create a fork that drifts away from the source. You stay on the upstream release train. When the central team updates, you evaluate it, you upgrade or you stay on your version, but you never customize. That discipline prevents maintenance debt from piling up across your tenants. Multi-tenant design reveals the limits of centralization. The more tenants you have, the more coordination you need. Eventually, centralization becomes a bottleneck. That's when organizations shift to a federated model. Each tenant owns its own modules and consumes from others through process, not through shared registries. The architectural question is what's shared and what isn't. That answer determines your entire governance model. Measuring landing zone health, KPIs that matter. You can't improve what you don't measure. Most organizations measure activity. They track how many policies they deployed or how many resources were created. Activity metrics feel productive, but in reality, they're just noise. What matters is the outcome. You need to know if your landing zone is actually helping teams or just creating the illusion of control. Provisioning time is the best indicator of governance health. This metric is non-negotiable. It answers the one question that matters. Can teams use the platform at the speed of their business? You must measure the time from the initial request until the infrastructure is ready for a workload. This isn't just about creating a subscription. It's the full journey from the vending machine through validation and configuration. The industry baseline is under 30 minutes. If you are measuring in days, your governance is a problem. If you are measuring in hours, you are close, but you aren't there yet. Provisioning time compounds. When a team waits 5 hours for a resource instead of 30 minutes, they lose a full workday. That is lost shipping velocity. That is developer frustration. That is exactly where Shadow IT starts to look attractive. This metric isn't just operational, it's strategic. It tells you if teams will use your platform or build around it. Policy compliance needs context to be useful. The number by itself is almost meaningless. 98% sounds great until you look at what you're measuring. If you're checking for tags on a VM, that 2% gap might be fine. But if you're measuring whether critical databases have encryption, 98% is a total failure. The metric matters, but the threshold matters more. Track these rates month over month. If compliance stays at 98%, your environment is stable. If it starts dropping, something is wrong. Teams are getting less careful, or your policies are becoming impossible to follow. A downward trend is a diagnostic signal. It means your policies aren't practical or your enforcement is broken. The number shows the problem, but the trend shows if you're actually fixing it. Configuration drift is governance breakdown made visible. You designed a hierarchy and assigned your policies. Then 6 months later, someone manually changed a setting. Someone created a subscription in the wrong place. Someone assigned a role directly instead of using inheritance. The environment drifted away from the design. Drift happens. The only question is how fast you catch it. Measure the percentage of resources that actually match their intended state. Automated tools should scan and compare your resources to the desired configuration. If 5% of your resources have drifted, you finally have visibility. What you do next depends on the change. A team enabling extra logs for debugging is fine. A security group being open to the public is not. Time to remediate tells you how fast you respond when things break. Once drift is detected, how long does it take to fix? If it takes weeks, the drift piles up. If it takes days, you're responsive. If it's automated, the drift only lasts until the next policy cycle. This metric proves whether your governance is reactive or proactive. Shared services uptime is a governance metric, not just an operational one. If your logging workspace goes down, you are flying blind. If your policy engine is unavailable, your rules stop being enforced. If your identity system fails, your deployments can't authenticate. Governance collapses when these services fail. You have to track it. Developer satisfaction correlates with productivity more than almost any other stat. Survey your teams. Ask them how easy it is to deploy or how fast they get support. If satisfaction scores decline, teams are losing confidence in the platform. That is when Shadow AT takes over. That is when teams start building their own alternatives. These metrics aren't just for a dashboard. They are diagnostics. They are how you understand if your landing zone is actually working. These numbers should drive the next evolution of your model. The evolution trap. Why landing zones become stale. Landing zones designed 5 years ago were built for the world of 5 years ago. Virtual machines, web applications, databases, containers. These were the standard patterns everyone understood. You could build a hierarchy that handled them perfectly. Your network design made sense, your storage strategy worked, and your compute quota stayed within reasonable limits. Everything fit the model. Then the world shifted. AI workloads arrived. Machine learning pipelines started demanding massive GPU clusters. Foundation model inference required specialized hardware that didn't exist when you started. Data science workflows began moving terabytes of data between regions just to handle training and inference. These workloads don't fit the old patterns. They break the structural assumptions you built into your landing zone. For example, an old landing zone might have a policy that only allows standard compute SKUs in dev environments. That policy was smart when dev meant testing simple web applications, but it fails the moment a data science team needs to test on the same high-end hardware they'll use in production. The policy stops being a guardrail and becomes an obstacle. Teams start requesting exceptions. Eventually, those exceptions become the rule. And once that happens, the policy itself becomes meaningless. The network design that worked for app deployments also fails when it meets AI. A machine learning pipeline needs to move data from storage to compute and back again, and it does this constantly. In your old design, all that traffic is forced through a central firewall. The cost, the latency, the architectural friction. It's prohibitive, but by the time you realize this, you've already built the firewall and connected every resource to it. You've already written the policies that assume this is the only path. Changing it now requires a full redesign, and redesigning at scale is expensive. The compute quotas you set are suddenly too restrictive for modern work. A team might need to scale an AI workload to 100 GPUs, but your hard quota only allows 10. That limit was reasonable when you were thinking about application servers, but it's absurd for machine learning training. To change that quota, you have to change the management group policy, which means you might affect other teams, which requires coordination, which requires approval. It takes time. The cost of redesigning after you've deployed is exponentially higher than designing for evolution from the start. You already have infrastructure in the wild. Teams are using it. Workloads are running. Changing your network topology now means potential downtime. Changing the hierarchy means moving subscriptions and reevaluating how policies are inherited. Changing quotas might even force teams to migrate their existing resources. Every single change carries an operational cost and a massive coordination overhead. Organizations that design for evolution from the start have a different experience. They build versioning into their landing zone from day one. They create clear deprecation policies. They document the migration paths. When a new workload type like AI appears, they evaluate if the landing zone needs to change. They release a new version. They publish a migration guide. They give teams a window to upgrade. Teams opt into the new version when it actually makes sense for their specific workloads. Versioning is the mechanism that allows for safe evolution. You treat the landing zone like software. Version 1 supports your traditional workloads. Version 2 adds support for AI. Version 3 introduces specialized networking for high-performance computing. Teams can stay on version 1 if they don't need the new features, or they can choose to upgrade. The path is documented and the breaking changes are already known. Migration is supported, but it isn't forced. Deprecation policies are how you avoid the nightmare of running 8 versions in parallel. You might support version 2 while you're releasing version 3. You give teams 6 months to move from 1 to 2. After that window closes, version 1 is officially unsupported. No new deployments are allowed on the old version. Existing ones can stay, but they're no longer considered current. This creates a natural pressure to stay updated without forcing a crisis. Migration paths act as the operational bridge between these versions. You don't just announce a new version and walk away. You provide the steps, the tools, and the support. You run the training sessions and answer the hard questions. Teams will need help moving subscriptions or reconfiguring their policies. You make that help available. The goal is to keep the platform current without forcing every team to move at the same time. Some teams will upgrade immediately because they need the new power. Others will wait because their workloads aren't affected by the changes. They upgrade when it's convenient for them. That distributed timeline spreads out the operational load, so the platform team isn't buried under support requests. Teams get help when they need it. The platform evolves. The teams evolve with it. But this evolution is only possible if you build for it from the start. That's the inversion. You don't design a static landing zone and hope it stays relevant. You design a versioned platform. You build flexibility into the hierarchy and plan for workloads you haven't seen yet. You build a mechanism for safe change, and that mechanism is what keeps you current when the world inevitably changes. The decision framework, when to centralize, when to distribute. The biggest mistake organizations make is treating centralization and distribution as opposing philosophies. One side fights for centralized control, the other fights for decentralized autonomy. They debate as if you're forced to pick a side. You don't. The right architecture centralizes some things and distributes others. The real discipline is knowing which is which. The framework is simple, but it requires total clarity. Centralize what must be uniform: security baselines, compliance controls, identity systems, encryption standards, the core infrastructure that everything else depends on. These aren't matters of opinion, they are the non-negotiable foundations of the environment. When you centralize these, you ensure the organization is consistent. You guarantee that a resource in one region meets the same security bar as a resource in another. You stop the compliance variance that makes audits a nightmare. Core services like network connectivity and shared logging must be centralized. This isn't just because it's easier to manage, it's because distributed identity systems don't trust each other. Distributed logging creates massive visibility gaps. Distributed networking leads to routing conflicts. The cost of distributing these core pieces always exceeds the benefit of the autonomy you think you're gaining. So you centralize them, you build them once and you build them well. They become the foundation that every other team builds on top of. On the other side, you distribute what must move fast. Product decisions, application architecture, local data models, experimental workloads. When a product team needs to choose between Cosmos DB or a managed PostgreSQL instance, that's their call. It shouldn't be a central decision. If an engineering team wants to try a new language or a different framework, that's their choice to make. When a data science team needs to tweak their ML pipeline, they should have the responsibility to do it. Distribution here is what enables speed. Centralizing these choices would only create bottlenecks. The hybrid model is where the real work happens. Central policy with distributed execution. You set the policies at the center to define the boundaries. Resources must be encrypted. Traffic must follow approved paths. Identity must plug into the corporate directory. These are the rules of the road. But the specific implementation, how a team encrypts their data or which key vault they use, is distributed. Teams decide how to meet the policy. They don't decide whether to meet it. This requires a shift in how you think about control. Traditional control is prescriptive. Do it exactly this way. Use this specific template. Follow this configuration. Distributed execution is focused on the outcome. Achieve this security result. Meet this compliance requirement. How you get there is your choice, as long as the final result is correct. The trade-offs here are very explicit. Centralization buys you consistency and enforces your standards. It reduces variance and guarantees everyone is moving in the same direction. But the cost is speed. Decisions take longer and implementation requires more coordination. Distributed execution buys you that speed back. Teams don't have to wait for central approval or fit into a rigid template. The cost here is variance. Different teams will do things differently. You'll need stronger monitoring to catch mistakes and better systems for managing exceptions. To make this work, you have to make these decisions explicit. Create a governance decision document, not just a list of policies. A document that clearly states what is centralized and why. It should explain what is distributed and why. And it should define how you'll revisit those choices. Then, you actually have to revisit them. Check in quarterly or annually. Look at it whenever the organization changes or new workloads emerge. Maybe you discover that something you thought you could distribute actually needs to be centralized. Your organizational maturity will shape what you can safely distribute. A young organization with limited engineering depth can't distribute much. The teams don't have the experience yet to implement standards on their own. They need those prescriptive templates. They need central enforcement to stay safe. But as the organization matures, you can start pushing more power to the edges. Teams gain the expertise to implement policies themselves. They develop the discipline to follow outcomes without needing a step-by-step guide. This maturity assessment has to be honest. It can't be aspirational or flattering. It has to be real. What is your actual capability right now? Based on that reality, what can you safely hand over to the teams? As their capability grows, your distribution expands. That's the evolution. The framework is what allows that progression to happen. The decision isn't permanent. It changes as the organization grows and as threats shift. It changes as new technologies appear and as teams prove they can handle the responsibility. The framework gives you a way to make these decisions on purpose. It stops you from drifting into a model that only exists because nobody ever stopped to question it. This framework is what leads you directly into the implementation. Building for the next 5 years, future-proofing your design. Landing zones aren't destinations. That's the fundamental misunderstanding. You don't build one, deploy it, and declare success. You think you've built infrastructure for the next 5 years. Wrong. Landing zones are foundations. They're meant to support what you don't yet know you'll build. And that requires a different design philosophy than optimizing for what exists today. The problem is obvious in retrospect. You design for virtual machines because that's what you deploy now. You design network paths for web applications because that's what your organization runs. You set compute quotas based on current usage patterns. These are all rational decisions based on your current reality. But then, machine learning arrives, or GPU-intensive workloads, or real-time data streaming at scale, and suddenly, the foundation you built doesn't accommodate these things. The network topology is wrong. The quotas are insufficient. The storage strategy doesn't work. You could have anticipated this. Not perfectly, but you could have built slack into your design. Not slack as in looseness, slack as in deliberate unused capacity, deliberate flexibility, deliberately simple decision points that can evolve. Designing for unknown workloads starts with admitting ignorance. You don't know what you'll need in 5 years. So instead of building a structure that's optimal for today, build a structure that can adapt. That means modularity first, not monolithic designs that assume specific workload types. You need modular designs that let you add new layers, new capabilities, and new patterns without re-architecting the foundation. You need a network design that can accommodate high-performance computing without changes. You need a hierarchy that can grow new branches for new organizational units without reorganizing existing ones. And you need versioning discipline as the evolution mechanism. You're not going to get this right on the first try. You'll learn. Technologies will change, and requirements will shift. So build the mechanism for safe change from day one. You'll use it. And when you use it, it won't feel like a burden. It'll feel like you're building for the reality of change instead of pretending change won't happen. Then, there is flexibility and constraints. Your policies shouldn't specify implementation. They should specify outcomes. Don't say all data must be stored in West US. Say all customer data must remain within regional boundaries as defined by compliance requirements. Now you can add new regions. Teams can deploy in those regions. The policy still applies. And you didn't have to rewrite it. You also need documentation that explains the why. You made design decisions. Why did you choose hub and spoke networking? Why did you structure the hierarchy this way? Why these policies? 5 years from now, someone will be evaluating whether to change these decisions. They need to understand the original reasoning, not to preserve it, but to make an informed decision about whether it still applies. Monitoring the horizon is how you catch when your foundation needs evolution. You're not waiting for things to break, you're watching. What new workload types are emerging in your industry? What technologies are gaining adoption in your peer organizations? What's changing in your regulatory landscape? What are teams asking for that your landing zone can't accommodate? That horizon watching is how you're proactive instead of reactive, because the cost of inflexibility is brutal. Organizations locked into outdated patterns have 3 choices. Redesign, which costs millions and disrupts operations. Work around the foundation, which creates the shadow IT problems we discussed. Or accept the constraint, which means missing opportunities. None of those choices are acceptable. That's why building for evolution from the start is structural. It's how you avoid these choices altogether. The shift from static templates to living infrastructure isn't just technical, it's organizational. It says you're designing systems that learn, that adapt, that improve, because you're collecting data and responding to it, not designing once and defending that design against reality. Landing zones work when they enable, when there are constraints that make sense, when the fastest path to compliance is the standard path, when asking permission is faster than seeking alternatives. Success isn't measured in how much you controlled, it's measured in how fast teams shipped, how many workloads started using the platform instead of building around it, whether compliance improved because governance was practical, instead of whether compliance improved because you were good at finding violations. Your first action, audit your current governance. Where's the friction? Where do teams wait? Where do they bypass? Those friction points are your diagnostic data. Fix them. The real work is harder, aligning organizational structure with technical architecture, making governance enablement instead of gatekeeping. That takes intention. It takes discipline. It takes leadership that believes agility at scale requires design, not control. Agility at scale is possible. You're building it now.